Our project is multi-sensor-based dynamic object detection, tracking, and trajectory prediction for self-driving. This is the continuation of a project from last year. We were supervised by Dr. Peshal Jayasekara and Dr. Ranga Rodrigo and funded by Creative Software. For a self-driving car, dynamic object detection and trajectory prediction is very crucial since in countries like Sri Lanka, incidents like jaywalking and sudden lane changes are abundant. We intended to detect and track several classes of objects such as vehicles, pedestrians, and cyclists. In our project, we take inputs through a camera and a low-resolution LiDAR. The camera images and low-resolution LiDAR point clouds are merged using sensor fusion, and a dense point cloud is input into the 3D object detection algorithm. The detection outputs are then input into the tracking algorithm, where a unique ID is given to each detected object throughout frames. Outputs of the tracking algorithm are used for signal detection and trajectory prediction. We will now go through each section of the pipeline. First, let's discuss about the detection model. The RGB images are fed into a 2D detection model while the sparse 3D point cloud is projected to a 2D plane. Then these points are matched with nearest neighbor matching. After that, a dense 3D point cloud is created by converting the obtained dense 2D point cloud. That dense point cloud is then input into a 3D backbone network from which map view features are output. Then, from a center heat map head, a regression head, and a velocity head, parameters such as position, orientation, and size are calculated. Now, let's move on towards tracking. We use the tracking algorithm of CenterPoint, which uses the Euclidean distances between path location and estimated path location, as well as greedy closest distance matching. A unique tracking ID is given to each object across consecutive frames. Here are some visualization outputs of our detection and tracking model. You can observe that the same color is given to the same object in their bounding boxes across frames. Since we are using a LiDAR point cloud based method instead of a camera image only method, we are able to detect and track objects under rainy and foggy weather conditions as well.
Predicting future paths of vehicles and pedestrians is known as trajectory prediction. For that, we use several inputs. Rasterized maps are used to ensure the predicted paths are in alignment with drivable and non-drivable areas. Fast trajectories of target and surrounding vehicles are also used. Multiple trajectory decoders output multiple future trajectories along with the scores. The trajectory with the highest score is the final output. We were able to reduce min AD and min FD values compared to the last year. In the visualizations, the green line is the ground truth and the red line is the predicted trajectory. The model is capable of identifying U-turns, junctions, and straight line trajectories very accurately. Based on our findings, we were able to submit a research paper to IEEE ITSC 2022. We were able to achieve the best results in using trajectory benchmark out of the models which use raster maps to input environmental information, and the 12th position in the leaderboard altogether. In the signaling detection part, we use consecutive time frames of the same vehicle to identify on and off state of brake, left and right signal lights. CNN and LSTM model is used for that. As you can see, the model is capable of accurately predicting those states. This is our conclusions and results. In this year, we used a camera image and LiDAR point cloud fusion method for detections. We were able to improve detection tracking accuracies and FPS rates significantly. We reduced the errors for trajectory prediction as well. We also added signaling detection and research paper submission this year.